Hello, so this is video number 1 of section 5.4. So last section we introduced diagonalization and this idea, of course, that we can find sometimes, right, the conditions we could impose on a matrix to show that that matrix is similar to a diagonal matrix. And so eventually in this section we're going to look at how diagonal matrices and similar matrices can be used to better understand linear transformations. But first I want to go over this video a little more terminology with respect to linear transformations and how we can start to better understand linear transformations between two vector spaces that might not be Rn and Rm. So I've got a little bit of preliminary material on the board here. So I'm assuming we have two vector spaces V and W. And again, we're not assuming these vector spaces to be sort of the standard, Rn, Rm style vector spaces. They could be anything. So polynomials, matrices, anything. And we're going to assume that B is a basis for V and that C is a basis for W. So we've each got bases attached to these two vector spaces. And next, we're going to assume that T is a linear transformation mapping V to W, and also that V is n-dimensional and W is m-dimensional. So remember, that means that this basis B contains n vectors and this basis C contains m vectors. So I've got our linear transformation pictured on the board here. And remember, from Rn to Rm, we can always find a matrix associated with any linear transformation. And ideally, we'd really like to do that with, any linear transformation from Rn to, yes, I said that. Anyways, ideally, we'd like to find some sort of matrix which can describe this linear transformation from V to W, other than just this definition T, which we've sort of imposed. But if the vector spaces themselves aren't vectors in the sense that we know vectors, right? So if they're not, the standard list of numbers, it doesn't make sense to multiply, for example, a polynomial by a matrix. Well, we have ways, remember, of associating n-dimensional and m-dimensional vector spaces with Rn and Rm. So remember that if X is in V, then we've got this vector called the B representation of X, which is an n-dimensional vector, or a vector of length n, because remember, this is corresponding to how we represent X as a combination of the B basis vectors. Right? So remember, what we know about this is that these vectors might not be traditional vectors, right? They could be polynomials or matrices, but these coefficients, the r's here, are just still scalars. And so we can encode these scalars in a vector. So for V and W, we have ways of associating these two vector spaces with Rn and Rm. And remember, this is the coordinate maps right here. So what this does is it sends all of the vectors in V to their B coordinate vectors in Rn. And then we can do the same thing with W. Where I'm going to send each of the image vectors in W, so this would be all of the vectors T of X, to C. And in fact, this would be all of the vectors in W, but at least at the moment, what we care about right now are the vectors that are actually in the range of T, right? So all of these vectors in the range would get sent to their C coordinate representations under this coordinate map. So now I want a matrix M which can send the B coordinate representation of X to the C coordinate representation of T of X. And this would give me, sort of in a sense, a matrix representing this linear transformation. Because remember, linear transformations, remember, like, we can now think of vector spaces not as like specific objects, but just as like coordinates relative to bases, right? So in a sense, these two vector spaces, again, are the same because we found these coordinate maps. And so this matrix M is, in a sense, performing the same linear transformation, right? Because we can sort of, if we wanted to eventually wind up here, we could go down here, multiply by M. We've now got the C-coordinate representation of the image of X. Well, and so then we can just find the original vector X in whatever vector space we are in. So I want to briefly talk about how we can find M. Try to leave all of the relevant information up. All right. So in order to find M, we should first look at T of X. So notice since T is a linear transformation, we can split T up across the terms. So what I've done here is I've represented X as its linear combination of B basis vectors. And what I can do is pull out all the constants like so. Right? So what I've done is I've just applied the fact that T is linear to split it across sums and pull out all of the scalars. So right now we are here, right? We've represented X, so all of these vectors live in W. And we've represented X now, or the image of X, as a linear combination of multiple vectors. Well, ultimately what we're looking for is the C representation of T of X. But remember, the coordinate maps are also technically linear transformations. So what I can do with this side and this side is apply the coordinate map and show that this is equal to the following sum, where I just take the C coordinate representation of the images of all of the basis vectors. And notice these scalars, R1 through Rn, come from the B representation of X. So what I've done is started with X, expressed it in its B representation, used that to express the image T of X as a linear combination of B basis vectors, and then I've applied this coordinate map mapping W to Rm to each of these basis vectors and applied the fact that that coordinate map is linear to get the following equation. Well, so each of these is a scalar matched up with a specific vector of length m. So if I let the matrix M equal the matrix whose columns are given by each of these C representations of the images of the basis vectors in B, then it turns out this matrix M is the matrix I was looking for down here. So I'll show you why in a second, but so notice that, again, this equation here gives me the C representation of T of X's, which is ultimately what we're looking for, right? And we're looking for a way to get from here to here by matrix multiplication. So notice if I let M be the matrix whose columns are given by each of these numbered terms in order, then if you remember that x sub b is this vector, and look at each of the coefficients in this equation, by the definition of matrix multiplication, the C representation of x is equal to this matrix M, which I've defined like so, times the B representation of x. And so what I just showed is that this matrix M is exactly the matrix we were looking for. So if I want to, in a sense, take two arbitrary vector spaces, one of n-dimensional, one being n-dimensional, and one being m-dimensional, what I can do is I can look at their B and C coordinate representations under any bases B and C I pick, look at this matrix M, defined like so, where I take the C coordinate representations of the images of the basis vectors in B, and let that matrix be, let those define the columns of M. And so notice in particular here, there are n total columns, and m rows. And so sure enough, this matrix M is in fact mapping Rn to Rm. So this does match up with a matrix that would be mapping Rm to Rn. So each of these are the coordinates needed to represent the images of the B vectors under this C basis for W. And so we call M, I'll find a place to define M here in a second. Maybe I'll erase the image so I can quickly define M. I'd highly recommend drawing this diagram. It's always what kind of keeps me, I guess, grounded in these chapters. So I find chapter 5.4 personally to be one of the most confusing chapters in all of linear algebra, just because, as you can see, the notation is very heavy. I'm not a huge fan of like super heavy notation. So I'm about to erase this. So this is also on page 291 of your book if you want to copy it down. But moving forward, I'd highly recommend you have this diagram handy. So like I said, the diagram often keeps me sort of focused on what we're trying to do, because there is sort of a lot going on here, and it's extremely interesting because what I basically just showed is that, well, I guess not me, but someone showed, and then I copied what they did in the lecture. That basically, we showed originally that remember that like any linear transformation from Rm to Rn is, or from Rn to Rm, can be represented with a matrix, and we kind of just showed that here for any two vector spaces, right? And that's because, again, we can think about vector spaces, as we showed, as just sort of arbitrary combinations of bases vectors, right? And so remember, that was sort of one of the big things we showed in chapter 4, right? Was that vector spaces you don't want to look too closely at the objects contained in vector spaces, right? That if you sort of look one level higher at how are the objects interacting and how can we describe these objects using these finite bases, we learned that any two vector spaces with a basis of size n basically look the same as long as you don't look at the objects too closely. And so for that reason, as we just showed, using that coordinate map where we say, okay, how are these bases interacting, we can always associate an n-dimensional vector space with R sub n. And so for that reason, we've got this matrix which can map the coordinate representations to each other. And then since we can always work our way back up from the coordinate representations, we always sort of have this matrix which can, in a sense, describe any linear transformation. And so, as I put here, this matrix M is called the matrix for T. I'll erase that. put those two words out of order. The matrix for the linear transformation T relative to bases B and C. So this is matrix M. And so to find M, you'll have to be given the two bases, as well as some more information about the linear transformation. But as we'll see, this section is kind of hilarious because the definitions in the diagrams are probably the most challenging parts of this section. Certainly keeping track of what's going on, but as you'll see, the problems that the book gives us, well, especially the problems that the book gives us, tend to be pretty straightforward. So let's look at an example of what we might see. All right, so what's cool now is that we're going to define two vector spaces, and we don't even know what they really are describing. We just know that one has a basis of size 3. So B1, B2, and B3 is a basis for a vector space V. We're going to let D be a basis of size 2, is a basis for a vector space W. Next, we're going to let T map V to W. And we're given three properties about T. In particular, we're given the images of the three basis vectors, B1, in terms of the three basis vectors for W. And remember, again, all we really need to describe the structure of vector spaces is what's going on with their basis vectors. So what we're given here are the images of the three basis vectors for V expressed in terms of the two basis vectors for W. And so what we want to find two things. The matrix for T relative to the bases B and D. And next, if I've got a vector X whose B representation is vector 1, 2, 3. So this vector X, I'll say where X is in V. We want to find the D representation of T of X. So we want the matrix for T relative to B and D. And then we're given this vector in V along with its B representation. And so we actually want to use this matrix M, which we're going to find first, to calculate the D representation of the image of X. All right, so remember, M is the matrix whose columns are given by, and actually maybe I'll do these problems so I have a little more room. So I'll put the second problem up on the board in a second once we find M. So the matrix for this linear transformation is the matrix whose columns are given by the D representations of the three basis vectors, or the images of the three basis vectors, so M is going to be a matrix with three columns, where this is the D representation of T of B1, D representation of T of B2, D representation of T of B3. I have all of those because we're given the images of the basis vectors, right? So column 1, I want the ordered coordinates attached to the two D vectors needed to represent the image of T of B1, but this is just 3, -5, because we have that. Also, this is just -1, 1, and this is just 0, 4. Right? So this is the first column, this is the second column, this is the third column, and that's it. So all this problem was asking to do basically was just to put these three images sort of in a matrix in the right way. And we've got our matrix M for T relative to B and D. So now if our vector X had B representation 1, 2, 3, well, we know that the D representation for T of X is just equal to this matrix M times the B representation for X, right? So basically what this matrix is doing is taking the B representation for X and turning it into the D representation for the image of X. Oh, and so as you can see, if I can do the addition right, which I probably can't do that in my head, so I'll just use my notes. This is actually also not terribly hard once we have this matrix. We get that the D representation for the image of X is equal to 1, 19. And so remember, that means that this vector, whatever it may be, is equal to 1 times D1 plus 19 times D2. So yeah, the problems for this actually aren't terribly involved. It's more just the, well, as you can see, it's more just the, kind of notation that can sometimes be confusing. So we've got a little more to do this video, and then I want to look at one more example. Well, actually, you know what? I think this video is getting long enough for now, so I'll stop video 1 here. We'll pick up video 2 with sort of this next, one more example and one more kind of idea, and we'll kind of keep moving forward with this.